Hi friends, welcome to something called science.com. In this video, we'll talk about the fascinating topic of the highest known oxidation state. You can find a full transcript on our website. A big thank you to our Patreon members. You are all awesome and helping out the channel a lot. So before we dive into record-breaking chemistry, let's understand what an oxidation state actually is. Think of it as a bookkeeping system that helps chemists track electrons in chemical reactions. When an atom forms bonds with other atoms, it can either share electrons, give them away, or take extra ones. The oxidation state is a number that tells us how many electrons an atom has effectively lost or gained. For example, in table salt, NaCl, sodium has an oxidation state of +1 because it gives away one electron to chlorine. Chlorine has an oxidation state of -1 because it takes that electron. So why do oxidation states matter? Well, oxidation states help us understand how chemicals react, how batteries work, why iron rusts, and even how our bodies process energy. When something oxidizes, like an apple turning brown or metal rusting, atoms are changing their oxidation states by losing electrons. Most elements stick to relatively modest oxidation states. Sodium is almost always +1. Calcium is typically +2. Even transition metals, which are more versatile, usually range from +1 to +6 in their common compounds. But what if we push chemistry to its absolute limits? How high can we go? The current record holder in terms of oxidation numbers is iridium, which is a rare and precious metal that achieved an astounding oxidation state of +9. This means that a single iridium atom has a formal oxidation state of +9. In the bookkeeping system that chemists use, we count it as having given up all 9 of its chemically active outer electrons. It's important to understand that oxidation states are a useful accounting tool rather than a literal description. The actual bonding involves significant sharing of electrons between iridium and oxygen, not a complete transfer. But for keeping track of electrons in reactions, we treat it as if iridium lost 9 electrons. Scientists created this remarkable species called tetraoxoiridium-9, or IRO4+, in 2014. However, this is not something that you'll find sitting in a bottle on a lab shelf. This compound can only exist under extremely special conditions, created in the gas phase using sophisticated equipment that can detect and analyze individual molecules. Think of it like this. Imagine trying to pull 9 people away from a crowded party where they really want to stay. It takes an enormous amount of energy and very specific conditions to make it happen, and the result is highly unstable. The next time you see rust forming on metal or an apple turning brown, remember, those simple oxidation reactions happening at +2 or +3 are distant cousins to the extreme chemistry happening at +9. It's all part of the same fundamental process, just taken to its absolute limit. While you won't encounter oxidation states this high in everyday life, or even in most chemistry labs, they remind us that chemistry still has surprises in store. Even after centuries of study, we're still discovering new extremes and expanding our understanding of how atoms can behave. Now, iridium isn't alone in achieving extraordinary oxidation states. Several other elements can reach +8. Osmium forms osmium tetroxide, OSO4, a compound that's actually stable enough to use in laboratories, although it's quite toxic. Each osmium atom bonds with 4 oxygen atoms and reaches the +8 oxidation state. Xenon, a noble gas that's supposed to be unreactive, can also reach +8 in compounds like xenon tetroxide, XeO4. This surprises many people because noble gases were once thought to never form compounds at all. Ruthenium can achieve +8 as well, showing that reaching extreme oxidation states isn't just a one-element party trick. So the +8 oxidation state is rare and typically observed only in certain transition metals like osmium, ruthenium and iridium, and in xenon, a noble gas. Now you might wonder, why can't we go higher? Why stop at +9 and not go to +10 or even +15? The answer lies in the fundamental structure of atoms. Atoms only have so many electrons to lose, and pulling away electrons gets harder with each one you remove. The first electron might leave relatively easily, but by the time you're trying to remove the 8th or 9th electron, you're fighting against enormous electrical forces. Additionally, oxygen is crucial for achieving this extreme oxidation state. Oxygen is highly electronegative, meaning that it's extremely good at pulling electrons away from other atoms. Even with oxygen's help, there are practical limits to how far we can push atoms. Some scientists have claimed even higher oxidation states, like +10 for platinum, but these claims remain controversial and difficult to verify. Now you might think that this is just chemists showing off, but here's the exciting part. Pushing chemistry to its absolute limits often leads to unexpected breakthroughs. Think about it. When engineers test how much weight a bridge can hold before breaking, they're not planning to build bridges that collapse. They're learning exactly where the safe boundaries are. The same principle applies here. By discovering that iridium can reach +9, scientists are mapping the extreme edges of what's chemically possible. This knowledge has already influenced the design of better catalysts. For example, understanding how metals like iridium, platinum and osmium behave at extreme oxidation states has helped improve the devices in cars that clean up harmful exhaust fumes before they leave the tailpipe. These devices work by shuffling electrons around in complex ways, exactly the kind of electron behavior we're learning about when we study extreme oxidation states. And there's another payoff. Sometimes the tools invented to create these extreme species turn out to be incredibly useful for completely different purposes. The sophisticated techniques that scientists developed to make and study tetraoxoiridium-9 have been adapted and refined for everyday laboratory work. Today, similar methods help doctors analyze proteins in blood samples, environmental scientists detect trace pollutants in water supplies, and forensic investigators identify mysterious substances at crime scenes. What started as a quest to push chemical boundaries has become a workhorse technology solving real-world problems. Yesterday's impossible chemistry becomes tomorrow's essential tool. Summing up, the highest confirmed oxidation state is +9, achieved by iridium in a special compound that exists only under extraordinary conditions. This represents one of chemistry's extreme achievements, pushing an element to give up nearly all its outer electrons. You can find the full transcript of this video on our website. If you found this video helpful, don't forget to like, subscribe and hit the notification bell for more science content. It really helps the channel out. Let us know in the comments if you have any questions or topics you'd like us to cover next. Thanks for watching and see you in the next video.